The TLDR of this video, if you don't want to watch the entirety of this video, is that if you make a bigger battery pack and you wire it the exact same way, then it should work. Hey guys, David here. It is a really exciting day for us as Boosted Board riders because we get to do something that seems pretty basic, which is to double our range. And this is something that we otherwise wouldn't have thought was possible prior to this research. So I'm really excited to be sharing this research with you guys because it means that if you are technically savvy enough, then you can go ahead and make your own, because I basically show you how I made mine. Or if you're not so technically savvy, then there is hope for you in the future to increase the range of your boosted board one day. The best thing you can do if you're not technically inclined and you want to somehow increase the range of your battery pack is to come into our Discord and just stay updated with what's happening there, because that's where we would be announcing stuff first, and that's where we would be announcing an upgrade program if that's going to exist in the future. If you're here for a short, brief explanation, I basically made a battery pack that is twice as big as the original XR battery pack. And this is it over here. And using the same cells, if you double number of cells, then you are going to get double the range in theory. This is basically a generic 13S4P, that's 13 series 4 parallel battery pack, except that I did have to reuse the original temperature sensors because I frankly don't know if the BMS will work with any other temperature sensors. And so everything works about it. Of course, the battery indicator works, the communication between the boosted board and the ESC works. The TLDR of this video, if you don't want to watch the entirety of this video, is that if you make a bigger battery pack and you wire it the exact same way, then it should work, in theory. I will get into a lot of the technical details as I read through my research. So this is the point that if you're not very technically savvy, I won't be offended if you just hop off now. I am basically going to go through paragraph by paragraph to try to explain in plain English what is happening as much as I can. So there's going to be some techno speak, but also I hope that I can spend this time to articulate to you guys what it is that this piece of text actually means. So without further ado, this is discharge and charge behavior of boosted B2XR PCB with augmented battery pack, or just the double XR experiment. The abstract is really the same as the TLDR that I said at the beginning, that as long as you make the battery pack bigger, as long as you reuse the same wiring and the same temperature sensors, then it should work as intended. That's basically what it's saying here. And the reason why that is not generally super intuitive, moving on to the introduction, is that we know that there are what are called shunt resistors at the top right-hand corner of the PCB if we are looking at it this way. Over here towards a negative terminal, there are some shunt resistors. Now we speculated that these shunt resistors would have been used for keeping track of the capacity. So there are so let's say that there's a value that is put inside the software, and that determines the total amount of energy that is inside the battery that it remembers. So our speculation prior to this experiment was that the shunt resistors is used by the computer that is essentially on your XR battery, that there is this amount of energy left over. We speculated that because we noticed that the state of charge indicator, the battery indicator I should say, is very, very stable. It doesn't seem to fluctuate up and down like a lot of voltage-based battery indicators. So we took that as evidence that it is using the shunt resistors to keep track of capacity by literally just counting the amount of energy that leaves the system. Now this understanding, after we've experimented it, is not correct. It's not accurate, and we'll get into all of that later. So we want to be able to create testable hypotheses so we can say that this is true or this is not true. So I'm going to go over those right now. Experiment 1. the double XR battery with stock shunt resistors will have the same range as the XR battery. This so happens to align with how our current understanding prior to this experiment worked, that we assumed that because it's counting the amount of energy that's leaving the system, that the range of the double XR should be exactly the same as the single XR. And the alternate hypothesis, we get either more or less range than the standard XR battery if we double the size of the pack. The second experiment is about charging. So if we drain it from 100% to 0%, can we charge it back to 100%? So our speculation was that the battery is keeping track of the amount of energy coming into the battery as well. So we thought that it might have been possible that if the battery is sitting at 3 volts per cell, then if we charge it to 100%, it would only be around 50%. It would only charge to maybe around 3.6 volts or something like that, where it really needs to be at 3.9 volts to be considered, 3.95-ish volts to be considered fully charged. So that is a purpose of experiment 2. So one of them is that, the null hypothesis is that the double XR battery should charge to a similar voltage as the XR battery, and the alternate is that it will finish charging at a different voltage than the XR battery. All right. Experiment 3 is about the balancing. So we want to see what the balancing behavior is. So we have good documented data on how quickly the XR should balance, and so we can just kind of compare that to double XR to see what effect does increasing the number of cells in parallel has on the rate of balancing. Experiment 4 and experiment 5 we did not conduct, but we did write these hypotheses prior to every experiment. So the experiment 4 is that the double XR battery with additional shunt resistors would have the same range as the XR battery. This is very similar to the hypothesis in experiment 1, except we are changing the number of shunt resistors. And because our speculation at the time is that the shunt resistors are being used for the battery to understand how much energy is coming and leaving the battery, then if we double the number of resistors, that will half the resistance. And if we half the resistance, what it means is that for every watt hour of energy that comes out, only half of it is being recorded by the battery. And this is a problem if we don't make the battery pack bigger, but if the battery pack is twice as big and we double the number of resistors, creating half the resistance, then in theory we should be able to fool the battery pack if it is using the shunt resistors to keep track of the amount of capacity. We found out that this is not the case, so that is why we did not test out experiment 4 and experiment 5, and we'll get into more as to why that is much later in the document. All right, materials and methods. This is fun. So I basically describe how the XR battery is constructed, and then I go into how the double XR battery is constructed. Instead of an enclosure, I used this over here. So let me try to make some space on this table. So I'm going to try to demonstrate what I did at every single leg of testing. So what I did is that there's an XR battery in here now that I used for testing. So let me try to take this out. All right, so yeah, this box over here is a standard XR box that I use for shipping. So when you send in a battery for me to repair, then this is the box that I send it back in usually, because a lot of people don't have XR boxes. So this double XR battery just so happens to fit pretty perfectly inside this box, and then I can have this connector over here connect it into the double XR battery, and then I would go ahead and do the testing that I would need to do. So that is that's basically how I did the ride testing. So I didn't have to make an enclosure, but I did have to like find a way for me to consistently, well, keep the battery like still. And yeah, that's how I did it. I did want to measure the voltages throughout every leg of the journey. So basically what I did is unplug the balance connector every single time. I would first turn off the board, unplug the balance connector, and then after I unbalance balance connector, I plug it into basically a dead boosted XR BMS that has a Bluetooth BMS attached to the back of it, because there are some diagnostic pins that allow me to read the same voltages that the battery is reading. I should say that the battery management system is reading. So I was able to use my iPhone to read all the voltages on the XR battery and the double XR battery as I was doing testing. Oh, and this is a pretty picture of the XR. It's in black and white for me, so it's in color for you. Yeah, and here's the Bluetooth module. Again, it's in black and white for me, but pretend that it's in color. Both the double XR battery prototype and the XR battery are running on 217 firmware with an amnesia chip. So the reason why I have an amnesia chip installed is that it's kind of stupid, but sometimes when I have to plug this balance connector back into the battery, I need to unplug the balance connector to read the voltages, but now I need to plug the balance connector back into the original boosted BMS. So if I don't plug it in correctly, let's see if I can get it. All right, 3, 2, 1, here we go. All right, so sometimes the BMS will turn on, and if it doesn't properly read the voltages, okay, it did it correctly that time because it boots. But if I didn't do it correctly, then it would go into red light of death. In fact, I'm just going to unplug the balance connector and then just turn on the BMS, and it'll go right into red light of death. So if that happens for whatever reason, I'm out in the field, I can't exactly connect the slow way of doing it would be to connect the flash to my computer and then wipe the flash. But that didn't seem like a very convenient idea at the time. So if I install Amnesia, what I can do is that if I get red light of death from plugging the cable back in incorrectly, what I can do is then hold down the power button for 5 seconds and turn it back on, and there we go. I got a fully functioning battery again. And the good part about that is that it also sustains its state of charge. So like the battery percentage inside the app will be accurate after I do an Amnesia reading. Here is the route that I picked. I went 1.5 miles up the bike trail and then another 1.5 miles down the bike trail. Oh, and yeah, for the entirety of testing, I used speed mode 2. Partly because they were only 3 speed modes, because I used a boosted V2 ESC and I also used boosted mini wheels on a boosted V3 deck. So this is a Frankensteining of parts here. And yeah, that's basically what I used. Also, if you want to know more about the weather conditions in which I tested, I have a section in Appendix C. I can honestly probably just show you that right now. But yeah, here's the picture of the board in case you needed one. Here are all the weather conditions. Again, this is in black and white for me, but just pretend it's in color. It is a lot more legible when it's in color. And I used dark sky for the readout. So for experiment 1, I got a total of 17.5 miles of range, which compared to the 10.1 miles of range that I got from the XR battery. That is a 73% improvement from the stock XR battery. So that sounds pretty great on the surface. 73% improvement. It's also worth noting that there are literally double the amount of cells. So we will address this discrepancy later on in the discussion. I'm just gonna try to get through the results. In experiment 2, we went from 0% to 100%, and 100% was around 3.95 volts, and it took around 2 hours and 26 minutes for the main indicator to turn green. That's how we're measuring it. it's not like it would have been better if we used the Ride app and just monitor it and in like 10-minute intervals or something to be like, all right, how high did the capacity go? All right, and we wait another 10 minutes. Like we didn't do that, so maybe that could have been better. But again, trying to get through the data. So then after reaching 100% state of charge, so after the light up here turns green, the 217 firmware will start balancing. This is very different than 251. 251 will actually keep your battery indicator red until it completes to 100%. So that's why we mentioned the firmware behavior over here. And we noticed that the delta actually went up from 181 millivolts to around 195 millivolts. So that seems very strange, but we'll get into that more. And as I said, experiments 4 and experiments 5 were not conducted. All right, so first paragraph basically summarizes what I said earlier, that the shunt resistors are not used to keep track of capacity. So that there's no arbitrary limit that we know of from just doubling the size of the battery that we can tell that prevents us from using larger batteries. So the shunt resistors are not used to keep track of capacity, then what are they for? It is possible that based off of other state of charge algorithms that are available, I should say that other people use, they use the shunt resistors here to do more accurate state of charge readings, because in an open circuit where you have no load, it is pretty accurate to use the voltage of the battery to determine how much energy is left over. But when it's under load, like when you are riding, then the voltage will drop very dramatically. So the shunt resistors may be used to compensate for that drop, because it can understand how much current is flowing to the load, in this case, the motors, and if they know how much current is flowing through the load and they know the value of the resistor, then they can also measure the voltage drop and add that to the nominal reading of the battery when it's under load. The next paragraph basically says the same thing about charging as well. We don't have to worry about the BMS refusing to accept more energy to the battery if the capacity of the battery is doubled. So that is good news. It means that we can discharge all the way to 0%, and we can charge all the way to 100% and have it behave from a per cell voltage perspective exactly the same as an XR battery, except it takes twice the amount of time to discharge, basically twice the amount of time to discharge, and twice the amount of time to charge. What is a very key finding here with experiment 1 is that the double XR battery behaves very similarly to the XR battery when it comes to the actual nominal voltage of each cell. For example, it shows 100% at around 3.95 volts and 0% is around 3.5 volts. And it will continue operating until the voltage of the lowest cell drops below 3 volts. This behavior was found in both the XR and the double XR battery that day. So that is very good news, because we have not modified anything yet. The only thing that we did is that we made the battery pack bigger, but the actual PCB itself retains normal operation. Amnesia chip, it only just clears the red light of death if it happens, but everything else is unmodified. So this is very, very good news for us. So why didn't we do experiments 4 and experiments 5? Well, since we know from experiment 1 and 2 that the shunt resistors are not being used to determine state of charge by counting the amount of energy that leaves the battery, that tells us that it has a different purpose. We know it's there for a reason, but we don't know why that is. And so in a worst case scenario, if we doubled the amount of load resistors, the shunt resistors that are in the upper right-hand corner, then that may underrepresent the amount of energy leaving the system, which can affect the state of charge calculation. So imagine that you are riding and your battery is, say, at 80%, and then when you stop, it drops to 70%. That is something that could conceivably happen because if we are using the shunt resistors only to determine state of charge while the board is moving and being under load, then it is reasonable to speculate that the state of charge indicator may no longer be accurate under load while the board is being used. Of course, this could be pretty innocent, but also it could be pretty catastrophic if, say, the ESC is requesting more current somehow, and it has this CAN communication between the battery and the ESC. So the ESC thinks that it can pull more current because the battery is communicating with the ESC that there is only around half the current that is being pushed out of the battery. But the ESC doesn't understand the shunt resistor configuration, so changing the shunt resistors may cause some catastrophic failures like burnt motor windings or something like that. So experiment 3 is the balancing test, and it seems that it doesn't really want to balance. Like, we go from 181 millivolts to 195 millivolts delta. So that is from the difference of voltage from the highest cell to the lowest cell. And we see that the delta is actually getting bigger. We don't know why this is. We have only been balancing the battery for a little bit under, 46 hours. So according to Project Beam Break, thank you, Robert, by the way, the data shows that it should take around 2 weeks for a standard XR battery to balance out a 200 millivolt difference? Yeah, a 200 millivolt difference. So if it takes 2 weeks, then it could potentially take like 3 here. And, it takes about 2 weeks to recover a 300 millivolt delta. So if we assume that's going to take twice the amount of time, then it could take like 3 weeks or so right now. So it might be too early to tell. And now I get to talk about all the mistakes that I made during experimentation. I won't really call them mistakes, they're just shortcomings of the data that I was able to get. First of all, the distances were measured with GPS instead of just marking out the trail, and it was pretty inconsistent because I used the ride app every single time I hit start ride, but sometimes it just seemed like I was going a little bit further than where I started, so I ride from a start point to an end point, and I ride back to the start point. I should have the same start and end point each time, but every single time the ride app recorded a slightly different distance, and so I had to go a little bit further or a little bit less far to compensate for the GPS inaccuracy. Also, I only know the distance that ride gives me from with 1 decimal point of precision. So I could be going 1.59 miles and it won't roll over to 6 until I go an extra 1/10 of a mile. And I don't know because ride only gives me 1 decimal point. So that is a place where the data could be a little bit inaccurate. Also, the percentage that ride gives me in the app is in full integers. So I don't know if it's 100, I don't know if it's like 80% 0.1 or whatever. It doesn't give me that data. So that is also some place that I don't have a very high precision number for the state of charge. I do, however, have a pretty high precision number for the nominal voltage per cell, but I don't really know the accuracy of the BMS app that I use. I'm not sure what the error is there. As well as, I can say that the BMS that I used for the entire day, it seemed pretty consistent, so I'm not super concerned about that, but just letting you know that I don't know the accuracy of this specific piece of equipment. But I do know from the experiment that it's pretty dang consistent. User error is something I should also address, because if I'm going full throttle, then sometimes my thumb can slip, and so for that split second in time, it's not full throttle. So that's something that I probably should say, because that's a possibility as to why there might be some discrepancies in the data. Belt tension. So the belt tension of the board didn't change, but I do have a slightly torn belt on one side, and like if you have if the belt tension is not as tense, then you typically get more range at the sacrifice of braking power. So I'm not so clear whether or not the fact that the belt is halfway torn has any impact on range, but just letting you know that's a thing that happened during testing. Changing weather. So I do have the data for the weather, but you can't really do much with the data, I realize, because I don't know in real time what direction the wind was headed towards me, nor my orientation in respect to the wind. So it might be hard to compensate for that. So there you go. Also, I do record timestamps in my lab notebook as well as on my laptop when I do just bench testing. And so there is some error there, I suppose, because I have to like write down the timestamp and then start my experiment or stop my experiment. So I might be off by a minute or like 30 seconds. That doesn't really seem to have a big impact on the data because it seems that the data points are pretty far apart. They're not a minute apart. They're usually a few minutes apart or a few hours apart in the case of balancing. So I don't think this has a huge impact on the results, but letting you know that might cause some skewing. All right, it is conclusion time. So we have determined that the null hypothesis is, we should reject the null because we get a different range as the XR battery. For experiment 2, it seems that we want to not reject the null hypothesis because it seems that we are able to charge the battery from 0% to 100% state of charge and have 100% be a voltage that is very similar to a standard XR battery. Yeah. For experiment 3, we want to reject the null because it seems that we're not sure, but we want to say that based off of our early data that it will take longer for the double XR battery to balance than the standard XR battery, since the delta is somehow increasing as time goes along. So this is unusual behavior, and we don't know what's up yet. And experiment 4 and 5, we're just going to cross off because, we didn't do them. So, future investigation. These findings are super counterintuitive to us because we totally expected that this BMS is programmed for one battery only. It is designed for one kind of cell only, and therefore if we try to make the battery pack magically bigger, it will snitch us out and not let us use the remaining half of the battery pack if we double the size of the pack. We totally expected that to happen, and that didn't happen, which is very good news, although we also don't know if there's an upper limit for capacity. Can we make a 13S 50p battery, assuming it didn't break your back? We don't know. We don't know if that'll work. We don't know if it will then lock us out or something, or if it's even practical to do so. So that's worth further investigation. Enclosure. That's a pretty important one because I don't think a lot of us would be down with just using a cardboard box mounted on the top of your board and call it a day. I could be wrong, but that also doesn't seem very safe, so I'm gonna elect to not do that. So we only understand that by making the battery pack bigger, that it behaves pretty much the same way as an XR battery. But we don't have an enclosure for it. So we have to do further investigation as to whether or not we have to do further investigation as to whether or not we can make an enclosure for it and have it stay on the board in a way that isn't just a cardboard box that's taped to the top of it. So we'll be investigating that. Heat generation. That's something that we don't have the proper equipment to assess. We know that there is a metal manifold inside the XR battery that is designed to dissipate heat. So Clearly, Boosted has thought about it, and maybe that is much more important in the summertime or where it's hot, because fish paper is not a very good conductor of heat. So I can imagine that if you are in a hot, if you're in a hot climate, then you would encounter some major overheating problems, or just some overheating problems. But that's something that we need to investigate further. Is this commercially feasible? This question is really important, mostly for you guys, and that's why I included it, because there's no point in us making this thing if we don't have any intention for this to somehow end up under your board. And I say that very tentatively because I definitely don't mean this exact battery. I mean a much more well-designed, battle-tested battery, and not whatever this is. It looks good, I know, at some angles, I can see how it looks good, but like it is not ready for human consumption for a very, very long time. But like that's something that we are going to assess moving forward to see if it's worth it to make an enclosure and to go through all of this engineering work in order for this to be a viable thing that you guys can actually buy or something. We'll see. Literature cited, yeah, go check out these guys. These are super cool dudes. Jonathan, super cool dude. Robert, I don't know yet, but you seem like a pretty cool dude. So, pretty cool dudes. Oh, and also, yeah, that's about it. Oh, I almost skipped the acknowledgments. Yeah, Jonathan, yeah, awesome. Awesome job. Robert, awesome job. r/boosted boards. You guys are amazing. I almost skipped, how could I do that? I almost skipped the acknowledgments. All right, so yeah, if you really wanted to know all of the cells that I used, here is all of the data. So I measured all of the capacities as well as the resistance of each cell before I put it in here. What else? And here are the instructions of how I made it. This is not a tutorial. This is just trying to show you guys how I made it. So if you want to replicate it, do it at your own risk, but I'm just telling you this is how I did it. It doesn't mean that you should do it. It's just showing you that for transparency's sake, as well as the balanced connection wiring and that. But you know, that is about it. Weather again, and here is all of the ride data that I gathered. So here are all the voltages, here's the timestamp, here is what the ride app told me, what the battery percentage was, here's the distance traveled, here's whether I use the XR battery or the double XR battery. What else? Oh yeah, and lab notebook. So this is basically exact same stuff. Oh, whoop. I'm so glad this is all on tape. I included the scans from my lab notebook, so you'll have all of this stuff inside that document over there. And what else is there? Yeah, and I think that's about it. So thank you guys so much. I want to say that this has been a journey, and I am really, really excited to see what comes out of this, because it turns out that making a bigger battery pack might be more technically feasible now than we have ever thought of before. If that I'm just tired, and it's Christmas Eve, or Christmas by the time I'm publishing this. Once again, the best place to support our work is simply by joining our community. It's a free community, and the whole reason why we're there is we're trying to keep our boosted boards alive, and now we're just going to try to make them even better. Thank you so much. Ride safe, always wear a helmet, and have a very, very nice holiday season.